this nice opportunity to introduce our research. I'm Shunji Kotsuki from Chiba University, Japan. And today, I'm going to explain our recent research on the data-driven sparse replacement method for designing better observation locations. And let me explain the motivation of my study. So I have been working on the FSOI study to evaluate the impact of assimilated observations, and this slide explains an example of the estimated impact. And through the FSO or FSOI, so we can evaluate the impact of assimilated observations. Here, this is an example, and we see the beneficial and detrimental observations. And so we would like to use the observation efficiently, and there have been many studies to assimilate observation efficiently, such as the treatment on R or treatment on the background error covariance. Alternatively, so our study proposes to place observation efficiently, and it can be done by the sparse replacement. And this next slide explains the concept of the sparse replacement method, so SSP, which is explored in the informatics science. And this is a method for optimizing the sensor locations using the sparseness behind the data. And so this is a famous paper by the Mama et al. That opened in the IEEE journal. And this SSP consists of the 3 steps. So, and I'm going to explain that these 3 steps using the data of the sea surface temperature. And so first we need to gather the training data, and we have a time series of the SST data for this example. And we employ the singular value decomposition to have a low dimensional mode, the first mode and second and third mode. And the SSP try to find the sensors that can explain the coefficients of each mode. And we can determine we can place observation. And based on these placed observations, we can measure the data, and we can reconstruct the field by data assimilation. And so the original sparse replacement employs these 3 steps, and here, so we use a sparse replacement for the sensor placement, and followed by the reconstruction by data assimilation. And here, the loading, reducing the dimension is very important, and for that purpose, we are using the singular value decomposition and widely used in the geosciences. And so this is one of the POD method. And so this is a method to extract the low dimensional features from high dimensional data. And this slide shows an example of the singular value decomposition. Also, we have a sea surface temperature data for the time series of sea surface temperature data. And we can employ the singular value decomposition to have a left singular vectors and right singular vectors and the singular values. And this rank is the number of the singular values equivalent to the rank of this like X matrix. But so we can reduce the singular vectors and the singular values to replace this data. And so in the case of the sea surface temperature data, so we can reconstruct the field only with the 10 mode. And such dimensional reduction is effective to reduce the model to reduce the problem size. And let's move on to the method to place observation. So we would like to estimate the state vector x, and based on the singular vectors, so we can replace this x vector using the multiplication of the singular vectors and its coefficient, and first singular vector and second singular vector to proper. And consequently, we can represent this state vector as a multiplication of the singular vector matrix and coefficient. And if we can have 2 observations, so we can represent these 2 observations based on this ways. So multiplying the observation operator to this x. And now this x state vector x is defined by this case, and we can represent this y by this CA2, where the C is observation operator multiplied to the left singular vectors. And using the least square regressions, we can estimate this coefficient. So if we have 2 observations, then we can estimate this coefficient. So the point of this dimensional reduction is that we can estimate state vector x when amplitude of A is determined. And the sparse placement finds observation placement to estimate the amplitude of A accurately. And the next slide explains the way. So we would like to determine this amplitude, but of course, so we can't observe the 2 state. And suppose the observation have a Gaussian noise, and following this equation, and also suppose the C is trustful. It means suppose the singular vectors are trustable. Then we can get this equation. The estimated coefficient can be obtained from this equation. And we will think about the error covariance of this coefficient. And here, so we can think about the error covariance of this coefficient. And through the linear algebra, so we can reach to this equation. Finally, so reducing this error covariance is equivalent to reducing this equation. And this is the case of the overdetermined problem, but we can do the same for the underdetermined problem. And consequently, so we can represent this error covariance of estimated amplitude by this inverse of Fisher information matrix, where the C is the HUR, observation operator, and the left singular vectors. And the equation is a bit different for underdetermined and overdetermined problem, but so reducing the error is equivalent to the reducing the inverse of Fisher information matrix, which is represented by the CC transpose inverse or the C transpose C inverse. And the sparse placement try to maximize the CC transpose or C transpose C that minimize the expected error in the estimate coefficient. Then we can have a good estimate on R. And there is several definitions of the reducing error of inverse Fisher information matrix. And there are three methods proposed previously from the researchers. And one is the so-called D-optimality, so that maximizes the determinant of this equation. And second one is similar to the Daiya assimilation of Kalman filter, so that try to minimize the trace of this matrix. And third one is that try to maximize the smallest eigenvalue. And the optimal criteria is case dependent, but the sparse placement finds observation place or observation flare H sequentially by greedy method based on these criteria. And I'm going to explain an example of the sparse placement based on the sea surface temperature data here. So the number of the grid point is over 40,000, and we used the 30 years of training data and followed by the test period for 2 years. And we used the monthly average sea surface temperature data. And so this right figure shows an example of the sparse placement. So here, so we place the 20 observations. And so this black circle is the placed observation by sparse placement. And the second example shows a random placement. And the third one shows the isotopical placement. And we construct the field from the observations. And we compare this estimation with respect to the reference too. And the color bar shows the error. And as you can see in this example, so we can estimate the state vector more accurately compared to the random or isotopical placement. And if we see the global mean root mean scalar over 2 years, the sparse placement shows the best estimate compared to random or isotopical placement. And so we applied this sparse placement for our problem. And today I'm going to explain the 2 experiments. So one is the radar precipitation, and the second one is the ensemble forecast data. And for the first example, so first experiment, so we would like to estimate the spatial pattern of precipitation based on the sparse placement. And here, so we use the 2 decomposition. One is a linear single value decomposition, and second one is non-linear, non-negative matrix factorization. And we place the rain gauge observation, and so we determine the static rain gauge observations and estimate the precipitation field. And the second experiment would like to place the adaptive radiosonde observation placement, and that will be explained later. Okay, let's move on to the first experiment. So this is a rain gauge placement based on the singular value decomposition or non-negative matrix factorization. And so we consider an experiment over Hokkaido Island in Japan. And here, this is the landscape of the Hokkaido, and we have an operational rain gauge station represented by this red dot. And we consider whether we can improve the placement. And we compare the so-called AMEDAS, operational control, operational placement, and sparse placement here. So we choose the number of mode and the number of observation for our experiment. And so for employing the singular value decomposition, so we need to have a training data. And we got the radar-based precipitation with modification of languages. And this provides a special pattern of precipitation. And we use this data for training. And we consider the 14-day accurate precipitation. And we use the 10 years for training and 2 years for evaluation. And here we can't measure the direct observation, and we can't measure the rainfall. That's why this observation are simulated by adding the Gaussian noise to this reference data. And we reconstruct the precipitation field using the data assimilation, and whose localization scale is tuned manually. And we estimate the spatial pattern precipitation and verify it against the radar-based precipitation. Okay, so this is an example of the placement. So here, so again, so left figure shows the placement of the operational languages, and the right figure shows the place where the Sparse placement suggests it would be useful. And we place a 200 language observations following operational placement. And based on this observational stations, we construct the precipitation field using an algorithm of LETK, and we verified it against the reference data. And these two figures show the root mean scalar against this reference data. And with conventional or operational languages, so we see the relatively higher error in precipitation in the mountainous regions. But we can place observation that can reconstruct field more efficiently compared to the operational stations. And if we see the root mean scalar, this Sparse placement can reduce the estimated error. So it means we can place observations efficiently. And so we use the singular value decomposition for this example, but recently we extended to the nonlinear dimensional reduction. And this figure compares the singular value decomposition and the so-called non-negative matrix factorization. And for the singular value decomposition, we decompose the data to the left and right singular vector with singular values. And if we employ the singular value decomposition or PCA for a series of face images, so we can see that this kind of the eigenfaces. And we can interpret the earlier eigenfaces, but interpreting the later eigenfaces is pretty difficult. But using these eigenfaces, so we can estimate the image of face by multiplying the amplitude of each mode into the eigenfaces. And for the non-negative matrix factorization represents data by only two matrices. One represents NMF vectors, and the right matrix represents each faces. And in the case of this NMF, so it have a constraint so that each NMF vector should be non-negative. So here, so this is an example of NMF applied for the same image data. And from this image, so we can interpret each mode. For example, that this NMF vector represents the face, eyes, and this represents the shape of our face or something. And we can also represent any state vector with the multiplication of the NMF vector and its amplitude. And this table compares this SVD and NMF and nonlinear decomposition and nonlinear decomposition. And in the case of NMF, so each mode is non-negative, and the importance of mode are equivalent in contrast to the single value decomposition. And also the lower mode is more interpretable compared to the single value decomposition. And this non-negative matrix factorization can be applied for the non-negative data. And we know the precipitation is non-negative, and we thought that this NMF is useful applied for the precipitation. And we applied it.
Warning.
Excuse me?
2-minute warning.
2 minutes.
You have 2 minutes left.
Okay, I see. Then okay, let's explain. So here, so we apply the single value decomposition, and this is the mode of the singular value decomposition, and we see the mean and para, like a left and right side balance. And but if we see the 50th mode, it's less interpretable. But if we apply the NMF for precipitation data, so each mode tries to capture the pattern associated by the orthogonal effect, and they seems to local precipitation patterns more correctly compared to the singular value decomposition. And we compare the singular value decomposition and NMF-based sparse sensing placement. And we made a series of experiments with respect to the different number of observations. And here we compare the isotropical placement and the singular value decomposition-based sparse sensing placement and NMF-based sparse sensing placement. And for every combinations, the NMF-based sparse sensing placement outperforms the other two experiments. So it means the NMF-based data decomposition is useful to capture the pattern of precipitation better than the other two methods. Okay, so I have an additional experiment, but I need to skip it. So we also applied the sparse placement for numerical weather prediction, but the concept is very simple. So we apply the singular value decomposition for the ensemble perturbation, and then we can determine the observational place adaptively or flow dependently based on the sparse placement. And the placing the observation based on sparse placement was beneficial. And we made an idealized experiment using the speedy model, but due to the time limits, so I will skip it. Okay, so let me summarize my presentation today. So today, we are proposing to combine the Taylor estimation and sparse placement, and that consists of the dimensional reduction and placement observation based on the Fisher information matrix and the data estimation for reconstruction. And we have been doing the experiment with promising result for sea surface temperature or radar precipitation. And so future plan is we would like to extend it for the more realistic numerical weather prediction systems. And also we have started to have a feasibility study with a railway company of Japan. Okay, that's all I have to say today. And thank you very much for your attention.
Thank you very much, Shunji, for this very interesting talk and also very promising results. There's one question by Lars. How do you obtain the modes for the non-negative matrix factorization?
Actually, we just use openly available algorithm, but this is actually this minimizes the difference between this X matrix and the multiplication of W and Z with unconstraint of the non-negative for each mode and each amplitude. And with iterative algorithm, so we can have NMF mode.
Okay, thank you. So I'm just checking the time and I see that we're a little bit behind schedule. So I would suggest that we continue the discussion in the Yopad. So I would encourage everyone who has questions to write a question. And Shunji, I would ask you to answer those questions in the Yopad if possible.
Okay, I got it.
Thank you very much. So thank you again, Shunji.